Okay, I made a mistake in lecture A, didn't catch it during class, but somebody caught it after lecture A. I made an algebra mistake. This should be an n plus 1 there, so it's e to the n plus 1 times r. Worked out in mathematical okay because I wasn't plugging in e, except at the beginning. That's why it worked out there. But this is the way the formula should look. That should go, replace that n with n plus 1. What about continuous income streams, cash flows? What about present and future values for those? The simplest kind of situation, it was the same situation we did last time. And that's where the payment stream, the cash flow, is at a constant rate. We call it P of T. It's the cash flow. Let's go ahead and assume it's constant, but let's not pick a particular number here. Let's go ahead and use the letter A. The constant rate of $A per year. In dollars per year, say, just to be specific. And by thinking about a number line and chopping up the number line into small little segments of length delta t, we derive formulas involving integrals for the present value and future value of income streams like this. This income stream is occurring over a time interval from time 0 to time m. Here's its graph. Its graph is at A. Since it's coming at a constant rate, the total amount of money you get actually is A times M. It's coming in at $8 per year. We saw that if A was 1,000, what was it, like 1 cent every 3 seconds or something like that? Or what? Maybe it was 100,000 actually, $80,000. So what we did before. In this kind of situation, the present value, I'll just call it PV for present value, was the integral from 0 to m of P of t times e to the negative rt. When P of t is a constant A, the integral looks like this. And this integral is not too hard to do. Antiderivative is going to be negative a over r e to the negative rt. Evaluate from 0 to m. And if you plug those numbers in and subtract and simplify appropriately, you're going to get a over r minus a over r e to the negative r m power is what you will get upon simplification. You can factor out the a over r if you like as well. That will be what the present value is. What's the future value? At time m, I didn't have time to derive it in class, but essentially you take that little chunk and push it forward in time. But if it's at time t, you're pushing it to time m, you've got to push it forward by m minus t years. And that results in an integral from 0 to m of P of t times e to the positive r times m minus t power. Once again, if we take P of t to be the constant A, you can write the integral like this. That wouldn't be too hard to do by hand. You may want to do a substitution, let w equal m minus t to help you do it. dw would be negative dt, and you'd want to switch the limits of integration upon doing that. And although you could actually get rid of the negative sign by switching them back, in order I'm talking about, maybe I should write down what that would be. If you do that substitution and use this equation to change your limits of integration, when t is 0, w is m. When t is m, w is 0. But then you can get rid of that minus sign by flipping around those limits of integration to be back in the original order. Oh, I guess this is not too bad. Let's go ahead and finish it. You never have to go back to t here once you've changed the variable like this. A e to the w from 0 to m. W is, okay, we don't have to go back there. looks like we get a e to the m minus a to the 0, which is just a. I don't think I made a mistake there, but where's the interest rate? Oh, I forgot my interest rate, sorry. There's an r here, there's an r here, there's an over r here. That looks like what it should be. Oh, and an r here as well. Yeah, got one more. Right there. Those are e to the r w powers, right? R times w. Sorry about those mistakes. Okay? So you should be able to derive these formulas in the abstract if you need to. Even in some other situations too. But I'm going to have Mathematica do it so we can get to as much content as possible. What if P of t is a linearly increasing function with average value equal to a? Whatever that constant a happens to be. Over a certain time interval from 0 to m, say. A linearly increasing function as time goes from 0 to m, whose average value is going to be a. That means the highest value is going to have to be 2a. And the slope of this line will have to be, rise over run, 2a over m. So the equation for such a situation would be P of t equals 2a over m times t. That'll be a linearly increasing function whose graph looks like what's on the board there. Integrating that times e to the negative rt would give you the present value. Let's clear r. We had a value of r stored earlier, so let's clear it. This should give us maybe, this should give us a formula involving r and m and a. I guess we didn't clear a either though. Clear a. Okay. Could that integral be done by hand? Yes. Could I do it but without making a mistake? Evidently not today I couldn't. Okay, I'm just making lots of mistakes. How would you do it by hand? That does involve a t in here that gets multiplied by the e. You'd have to use integration by parts. Evidently, for trusting Mathematica, this is the answer that you get. And then you can plug in particular a and r for a given situation. And you should be able to do that in a problem where you're given a, m, and r. How about a linearly decreasing function? Like that, whose average value is also a. The slope of this one is going to be negative 2a over m. What's going to happen in that situation? Probably something kind of similar. I mean, it will be different, technically speaking. There would be a formula for such a function. There's the slope. There's the vertical intercept. This integral is going to give you the present value of such a thing. Would the present value of this kind of thing be bigger or smaller than the other present value? The second case, you're kind of front-loading your money. You're getting it more right away and less later. And that front-loaded money doesn't need to get pulled back in time as much. The second one should be more, though it's going to be hard to tell just from the expression itself. Let's plug in specific values of a, m, and r in these things. I can do that like this. How about a is 1,000, m is 20, and r is 0.04. That one gives you 11,950. I think this next one down here, I'm going to copy and paste this thing here. I think this one should be bigger. And it is. Because that involves the second situation where you're front loading your money. It doesn't have to get pulled back in time to spot. Okay, and you could continue doing more kinds of examples. But you should be able to use this formula and this one in your homework. I didn't do future values here. I'm not going to take the time because I want to talk about actuarial present value. But we can certainly do them in that mathematical. Actuarial present value of a single payment. I've got two examples in here, and this is going to be another reason you're going to want to download this particular notebook. I will put this up on Moodle. I've got two examples. They're kind of long and complicated. I'm probably only going to have time to go over one of them today, and we'll go over the other one on Friday. One of them, I'm going to assume the lifetime random variable is uniformly distributed. PDF is a horizontal line. By the way, the real life situation I'm going to be imagining is a washing machine, okay? Capital T is going to represent the random lifetime of a random washing machine made by the same company, say. And we're going to talk about warranties on washing machines where you're going to get money if the washing machine breaks. So uniformly distributed, and we're also going to do an exponentially distributed. Let's do the uniformly distributed one today. The PDF is this. Okay, I've got the stuff on the screen, but I also think I want to write it on the board as we go to emphasize some things. Omega, it's not a W there, by the way, that's an omega. Mathematicians always make their W's pointy because if you write it like that, it's an omega. I won't get mad if you say W, but that's a 1 over omega. It's a common letter to use when your lifetime random variable has finite domain, essentially. The probability of getting past omega is 0. If your washing machine, working past omega. So the graph of this PDF looks like this. If omega is the maximum lifetime of the washing machine, to make it a PDF, you got to make the area equal to 1, remember. That means the height of the rectangle has got to be 1 over omega. So the formula for this function is 1 over omega when omega is positive and t is between 0 and omega. Omega is the maximum lifetime under this model. Not saying that's realistic, I'm just saying that's what the model is. Don't worry initially here whether things are realistic or not. Okay. That would be for people who actually have data, and we don't. What's the corresponding CDF? It's an antiderivative, not just any old antiderivative. It's got to go. Its graph has to go through the origin. Since these are lifetime random variables, we can do our lower limit of integration at 0 instead of minus infinity, like the book does in general for CDFs. What is a CDF? Again, this is the PDF here, little f of t. The CDF is used to compute probabilities. It's, in the abstract, it's the probability that your variable is less than or equal to that quantity t. Think of capital T as representing the actual lifetime of the washing machine. Think of t as being a particular instant in time that we're thinking about. We're wondering what is the probability that my washing machine will die before time t. It'll stop working. That would be what this represents, and it is an antiderivative of PDF. You can find probabilities by integrating the PDF, and for this probability, which is the same as this one for lifetime random variables, that's the way the integral would go. In this setting, when you integrate this function in this way, the formula for the CDF is t over omega. The graph of the CDF looks like this. It's a straight line with a slope of 1 over omega. And its value at time equals omega is 1. The formula for capital F is t over omega when t is between 0 and omega. It's an antiderivative of the red graph. Its derivative is the red graph. Right? The slope is 1 over omega. What's the mean and what's the median? Well, by the symmetry of the situation of the PDF is symmetric about a vertical line halfway through at omega over 2. That's going to be the value of both the mean and the median. The mean is the balance point. It's really the center of mass. You can think of means as being center of mass if you imagine the PDF as a graph that's representing a thin sheet of metal. An actual geometric thin sheet of metal whose total mass is 1. The mean is the center of mass. It's got to be in the center here because of the symmetry. The median is the point where half the area is to the left and half the area is to the right. Well, once again, by the symmetry, that's got to be omega over 2. And these calculations confirm it. Remember that you calculate the mean by integrating t times the PDF over the domain. So that's the integral that you got to do to calculate the mean. And if you do it, look, you get omega over 2. You can check this calculation. How about the median? It's time t med. This is not standard notation, by the way. It's the time where the CDF equals 1/2. The formula for the CDF is that. So set t over omega equal to 1/2 and solve for t. You get omega over 2 when you multiply both sides of this by omega. So that's not surprising. What's new here today now is we're going to combine this lifetime for a washing machine with a maximum lifetime of 20 years with a warranty. Now we're getting into actuarial stuff, insurance kind of thing. You're sort of insuring against your washing machine breaking by buying a warranty. Or maybe when you get the washing machine, you get a warranty, and that's part of the price of the washing machine. Pretend that if your washing machine goes kaput, that you get a benefit of $1,000. But when is your washing machine going to go kaput? It could be tomorrow, it could be a year from now, it could be 10 years from now, it could be, well, at most 20 years from now, according to this model, if you buy it right now. The amount of time the washing machine lasts, its survival time, its lifetime is random. And therefore, the present value of that $1,000 is random as well. What is that present value? It's this. Calling it Z because it's common to call it Z. Actuaries call it Z. That's a variable that's random. It's a random variable that represents the present value of that future payment that you will make to the customer when their washing machine breaks. Their washing machine is going to break, according to this model, sometime between time 0 and time 20 years. You don't know when. It's random. Whatever that random time, capital T, is, if you calculate this, assuming a 5% interest rate, compounded continuously, that'll be the present value. We're taking $1,000 and pulling it back in time by capital T years. But since capital T is a random variable, so is Z. What do you want to find? You want to know statistical kinds of things about Z, probability kinds of things, I should say. What is its distribution? Meaning, what's its PDF and its CDF? How do you find probabilities related to it? How do you find an actual probability? What is the probability that the present value is between $600 and $800? It's got to be less than 1,000, by the way, right? Because you're going to pay 1,000, and if the washing machine breaks as soon as you get home, the present value is the same as the actual amount that you pay, $1,000, because no time has elapsed. It's got to be less than 1,000. Can't be negative either, though. Can't be a negative present value. What is the probability that it's between $600 and $800? What's the mean of Z? In other words, the mean present value of the future payments for lots of customers. And what's the median? Okay, what I'm about to show you is the trickiest calculation of this. And I think I better just show you on the screen instead of writing it on the board. For sake of time, here we've got, what do we have here? I was forgetting. I guess we have 15 minutes. Okay. Now maybe I should do it on the board. We want to first find the distribution of z, this present value random variable. It turns out to be easiest to find the CDF first and then the PDF, which is a little opposite of what we've done so far. With the uniform distribution, with the exponential distribution, and with the other triangular distributions we considered before, we always assumed we were writing down the PDF first. Maybe based on some data set where we made a histogram, it's like a bar chart that shows us the shape of the data, the distribution. We made that first. Normal curve is another example. Look like a bell shape. Those are all PDFs. In this kind of situation, to figure out the distribution of this variable, it's easier to figure out the CDF first. Let's call the CDF capital G. The PDF is going to be little g. The random variable is capital Z. The input here I should probably call little z. By analogy with what I wrote there, and by what I've told you in the past, and by the fact that z can't be negative, I can always write the CDF in this way, but because z can't be negative, I can do that as an integral, starting at 0. For any variable, t, z, x, no matter what you call it, the CDF can always be thought of as a probability that your variable, in general I'll call it x, is less than or equal to some given x. Think of that as your random variable, think of this as a particular number. That's going to be the variable for the CDF itself. That's what I'm doing here. That's analogous to what I did here. And because t couldn't be negative here, I could start my integral at 0 instead of minus infinity, for example. And because z can't be negative either, I can start this integral at 0. Okay, these integrals that start at 0 are nicer than minus infinity ones, right? Because we don't think about improper integrals that way. Technically speaking, this would be the integral of the PDF, but I'm not going to calculate it that way. Let me go ahead and finish writing this anyway. What letter should I use? Let's use a cursive Z. How about that? Ever seen that before? It's not a Greek letter, actually. It's a cursive Z. But I'm not going to calculate it that way because I don't know little g yet. So instead I'm going to calculate it a different way. And the way to do it is to relate it to capital T. Here's our relationship. Use that. Replace the capital Z with 1,000, I'm using a 5% interest rate, e to the negative 0.05 capital T. What can I do with it? Through some algebra, I can relate it to this because I got a capital T. Essentially what you want to do inside the parentheses here is try to solve for capital T. Solve the inequality for capital T. And relate it to what you see up here. That's how we're going to do it. Bit of tricky algebra. You want to divide both sides by 1,000 first. Then take the natural log of both sides. Both such operations do not change the direction of the inequality. Dividing by 1,000 is dividing by a positive number. The direction of the inequality stays the same. Applying the natural log function to both sides to get rid of the e does not affect the direction of the inequality, and the reason is because the natural log function is an increasing function. This ends up equaling, after you do those two things, the probability that negative 0.05 times capital T is less than or equal to the natural log of z over 1,000.
Dr. Kenny, is that symbol before the P on the bottom a minus, a negative sign,
that's
or
an equal
equals? Okay.
Yep, thanks. So I did two steps there in one. I divided both sides by 1,000, then I applied the natural log function to both sides to get rid of the e. So that I can ultimately solve for t. I've got one more step to do. Divide both sides by negative 0.05, but if I divide by a negative number, the inequality switches direction. This is the same as the probability that capital T is greater than or equal to this divided by negative 0.05. Dividing by 0.05 is the same as multiplying by 20. So I could really write a negative 20 natural log of z over 1,000. Now realize, even though you see a negative sign here, that this quantity over here is actually a positive quantity. If z is between 0 and 1,000, which it is, then you divide it by 1,000, you get a number less than 1. And the natural log of a number less than 1 is negative times a negative, which is positive. This is actually a positive quantity in disguise here on the right. But as far as relating this to this, it seems, well, a little confusing because the inequality is going the wrong direction. That's a less than or equal to with the capital T to its left, and this is a greater than or equal to with the capital T to its left. So what do you do? Well, you use another fact about probability. Now the probability of something happening is 1 minus the probability that it doesn't happen. For example, if there's a 30% probability of rain tomorrow, that means there's a 70% probability of no rain tomorrow. 100% minus 30% is 70%. Or as a decimal, 1 minus 0.3 is 0.7. Therefore, I can calculate this probability by doing 1 minus the probability of the opposite event, which technically involves a strict less than sign like this. However, being a continuous variable and finding areas under curves means you actually can replace the strict less than with a less than or equal to, and you get the same probability. It doesn't matter, since we're dealing with continuous variables. There's a probability that deals with discrete variables as well, but we're dealing with continuous ones. Now it's in a form that I want. Compare it with this thing over here. It matches that thing if you replace the little t with this mess. Go ahead and do it. Replace it with that mess. Using the formula ultimately for capital F in this situation, which was this. We are dealing with T itself being a uniform distribution. There's the CDF. That's the capital F that I plugged this in for little t. I'm going to get 1 minus did I have something for omega? Omega was 20. Omega was 20. So we get 1 minus negative 20 natural log of z over 1,000 divided by 20. Omega was 20. I'm plugging that expression into here in place of little t, and I'm using the fact that omega is 20. Simplify, you get 1 plus natural log of z over 1,000. That's probably the best way to write it. It's not the only way you could write it. You could write that as 1 plus natural log of z minus natural log of 1,000 as well, using properties of logs. And actually, because of that, it's clearer to, if you write it that way, and in fact, I'll just put the constant here in front, it's more clear that the derivative of this, the PDF, is actually 1 over z. If you differentiated this, you'd get 1 over z after simplification as well. First you get 1 over z over 1,000, but then you can multiply by 1 over 1,000 by the chain rule, and the thousands would cancel. Little g of z here is 1 over z. Be careful about what the domain is, though. I was not really careful about the domain. And in fact, because the domain, it actually doesn't start at 0 here. If I was representing this as an integral, I wouldn't start at 0. I'd start at the lower endpoint of the domain. What's the smallest possible value z can be? The smallest z could be is if your washing machine lasts 20 years. The entire time before it dies. And the smallest value of z then would be what you get when you plug in t equals 20 right there, which would be 1,000 e to the negative 1 power. The domain here is 1,000 over e up to 1,000. It's the same as the domain for this one that we're thinking about. 1,000 over e to 1,000. That's the domain. And so actually, if I do capital G here as an integral, I'd have to replace this with 1,000 over e actually. That's the distribution. There's its CDF. Either this way or that way, doesn't matter. And it's PDF. Integrating PDFs gives you probabilities. Finding differences of CDF values gives you probabilities because that's an antiderivative of that. What do the graphs look like? There's the PDF graph. And 1,000 over e is the lowest value. And it's around 0.0027, I think. That's what 1,000 over e equals approximately. Great, wait a minute, that makes sense. What you get, it's e over 1,000 actually, is the highest value. Because you got to plug into the PDF, which is 1 over z. E over 1,000 is about 0.0027, which should make sense since e is about 2.7. What about the mean and the median? This is what we'll end with today. Just like always, the mean is found by integrating the variable times the PDF. Z in this case times g of z, little g. Yeah, and integrate from 1 over 1,000 to 1,000 because that's the domain. That actually is an easy integral to do because g of z, little g of z is 1 over z. The product of z and g of z is 1. My favorite kind of integral. Second favorite, I guess, for 0 would be my favorite. It's about $632 for the mean present value. The median can be found by solving this equation for z. Now use logarithms and exponentials. The median is about $607. The mean is actually more important here in terms of the insurance company's perspective. What is this telling them? This tells them if they expect to be able to get 5% returns on their investments, as an insurance company investing in the stock market, for example, that if they're going to be able to pay you your $1,000 benefit for lots of, not just you, but for lots of their customers, they better at least charge you this much for the warranty, which is pretty expensive for a warranty. Really, they'd want to charge you more because they'd want to make a profit.